I wouldn't be a good player on that show, I don't think. People would say the wrong thing and I'd get mad and sabotage them. I'm just saying. Okay, let's start talking right here, guys. First thing we're going to kind of do is this. We're going to look at finding volumes of a square pyramid. Guys, what's the base length they give you on this? 80 inches and a height of what?
55.
Okay, I'm going to ask you guys to do your best to try and draw a square pyramid. Okay, this is not an easy thing to draw. Okay, I would say start out like this. Kind of just start like that. Okay, can you make something like that? Okay, and then call this an 80 right here. Call this an 80. Okay, now for my pyramid, I'm just going to pick a point up here. All right, that's going to be like the tip of the pyramid. Is that okay? Okay, to draw my pyramid, I'm not going to get too technical with this. Oh shoot, I totally missed on that. Okay, can you guys kind of see the pyramid there? Okay, I picked a point up there and just connect each of those, the endpoints of that little shape that we drew down there. I think that's all you really need to have here, okay? So guys, here's what we have. We've got a pyramid that is going to have a square base, which is 80 inches by 80 inches. So down here they're saying this is 80 inches and this is 80 inches. All right? Now, the idea that they're giving us dimensions to this allows us to use formulas that have already been predetermined by the process we're about to start looking at today. But we're going to start looking at using geometry applications, finding volumes by what's known as slicing. We're going to slice this up into a bunch of little flat pieces like this. So if you can kind of imagine me going through here and cutting horizontally through this pyramid, if I could pull this section up, maybe the pyramid kept going, getting bigger and bigger and bigger. This one cross section, when I lift it off, what shape do you see right here? You see a square, right? Okay, so there's a lot of things that I'm going to talk about. There's going to be a lot of technical stuff that comes with this. But before I start this right here, I'm going to go ahead and put it in over here. Guys, what's the height of this right here?
55 inches.
Okay, so we're going to go ahead and draw this out first. It's got a height of 55 inches. Okay, are you with me on that? So we know we're dealing with a pyramid. Square, we want to find the value, all right? So let's just do this first. Somebody look at, or does anybody remember the volume formula for a pyramid? If it was a cube, 80 by 80 by 80 or whatever, you would have gone length times width times height. Do you guys remember how many pyramids with the same base and height fit into a cube?
3.
3 of them, very good. Okay? There was 3 of them that fit in here. So we could say the volume of any pyramid would be the area of the base times the height divided by how much? 3. Okay, just from this right here, I'm just going to say, based on formula, the volume of this would equal our length times our width. So in other words, 80 times 80 times the height, which is, what is the height there, kids? Is it 55? And since it's a pyramid, I divide it by what?
3.
Okay, I just want to go ahead and get the volume of this first, and then we'll start looking at how we're going to process through this kind of stuff, because some of the things that we start looking for volumes for, they're going to have some funky shapes to them. We're going to want to be able to find those volumes, okay? Somebody punch that mess in. 80 by 80 times 55 divided 3. Tell me what you've got for a volume.
117,333.33.
So 117,333 and a third, is that right?
Yeah.
And that would be square inches, wouldn't it? Okay, now again, if you didn't remember the formula for the volume of a pyramid, no biggie, look it up, you're going to need to know it. Okay? Here's how we're going to go about stuff today. All right? We're going to start looking at this as a bunch of little square prisms. Remember how I said I could take one square and stack on another, where the next square that gets stacked on top is going to be just a little bit what? Smaller. So the length and the width, as I move up, what's going to happen to the length and the width of those squares? They're going to get smaller and smaller and smaller. Okay. I need to review something with you. You might want to jot this down. What's the very back side of your notes look like? Is it kind of blank back there?
Totally blank.
Totally blank. Go to that totally blank side on your notes. Let's just review some things right here. Similarity ratios. Guys, if two figures are similar, they're the same shape, but what? Different sides. Okay, we're going to see things a lot like this. A lot's going to have to do with maybe some triangle stuff today. Okay, so I'm just going to make a triangle right here. If I tell you something like this, like maybe this is 15 down here, and maybe this is x. Okay. Furthermore, I'm going to tell you these two triangles are similar because this and this, they are parallel to each other. All right? That makes sense to you? How about I tell you the total, I don't know, maybe the total distance here is 62. And maybe the distance from here to here is some value y. Okay? When you have shapes that are similar, one smaller than the other, but they're the same shape, we can set up ratios or compare corresponding sides. So I might set up a ratio that says the following. I would say x is to what, kids?
15.
Okay, the shorter leg here in the small triangle compared to the corresponding leg in the bigger triangle. I can say x is to 15. That ratio should be the same as what over what, kids? That ratio should be the same as what other variables and values are up here? Okay, so that should be the same as I compared small value x to a bigger value 15. That ratio should equal y over what? Y'all agree with that? Okay, now, you're going to get asked today about some things. We're going to be in a situation where it's important to get everything written in terms of one variable. So I might say, I don't want x in there. So I might say, we've got to figure out how to write x in terms of y. Well, you guys know enough about proportions, don't you? If I wanted to get x alone right here, I would simply cross multiply and then do what? X, my friends, if that's what I'm trying to get alone, would equal what times what first? 15 times y all over what? So if I have an x in a function right here and I want to replace it with something in terms of y, I would replace x with what?
15y on the 16.
Okay. That concept is going to be used a lot today. Okay? Make sense? Okay. Let's get rolling on how we're going to handle things today. I'm giving you an example with a square pyramid first because we know we could use a formula to find the volume of a square pyramid. And we already know in the end of this right here, kids, that the volume is going to be, volume is going to be what value? Oops. What do we have?
17,000, blah, blah, blah.
Yep. Okay, that number right there, okay? Here's how we start going about this, okay? We've talked about slicing this up. So my slice is right here. I'm going to draw on my pyramid here, okay? You're going to see me doing a lot of stuff like this, like drawing a slice in here. Now again, is there some thickness to this slice right here that I just drew on this? Well, we have to understand the thickness of what we just drew is really, really close to what? 0. Okay? Things to think about as we move through stuff. Okay? When we start labeling things today, I'm going to put this way at the top. When I start labeling stuff, if I have some unknown that works left to right, we should probably call that some kind of an x value that we don't know. Therefore, if we're talking about some value moving up and down, we should probably call that some what value, kids?
Y.
Okay. Here we go. This is so cool. First thing I'm going to do is I like to come in here and I like to say, okay, let's pick out a slice. I don't care where that slice is. I'm going to say the slice goes here. And make it kind of, big enough so that you can see it. All right? But we understand that slice that I just took out of that pyramid, is that a big slice or a small slice?
Small.
Okay? The thickness of that is very, very thin, right? Okay? So what we say right here, guys, this is my slice. Now, the thickness of this slice, I don't know what the thickness is, but is that thickness vertical or is it horizontal?
Horizontal.
Okay, the thickness from bottom to top.
Oh, vertical.
Be vertical. So I'm going to say that this is going to be a change in y. I don't know what that y value is, but I know that y value is very close to what value?
0.
It's the limit, really, as y approaches what value? 0. It's infinitely small. I don't know how thick that slice is, but it can't be 0, it can't be nothing, but it's got to be something. So it's infinitely close to what value?
0.
Okay. Guys, when we start talking about this, you have two things to consider. Okay. First thing you want to start looking at is a three-dimensional shape, really in terms of a two-dimensional shape. So here's what I'm going to do. I'm going to come down here. If I'm looking at the pyramid from the front, basically the only thing you would see is a triangle. Do you guys agree with that? Okay. Here's what I want you to do. Draw your triangle. What's this length down here, kiddos?
80.
Okay. It is 80. And we know the height here again is how much, kids?
55.
Okay. And we have a slice in here somewhere, don't we, kids? And I'm going to color that slice in. I just want that slice. That slice is right in here. Okay? We said the thickness of the slice was, from top to bottom, delta what?
Y.
Okay. Okay, now I want to talk about this delta y here for a second. Guys, when you figured out how your slices are going, and sometimes your slices won't be horizontal, sometimes your slices will be up and down, like this. And we'll look at some examples like that in a little bit. But here's the deal. When you assign something to be delta y, our job is to write some function for this volume in terms of y. When you assign a delta something, that variable basically becomes the variable that you're going to go to, or write with respect to all time. Okay, now, this slice right here, this slice has to be less than what value?
80.
80. Is this slice running left to right here now? In other words, the length of the slice. Horizontal, isn't it? Wouldn't this be a distance x up here? Okay. Now, that slice can happen anywhere. It could happen here. I just chose to put it right there. Or that slice could happen up here. But the bottom line is this. If I start down here, what height am I really kind of starting at the very bottom? What would you consider bottom level or ground level?
0.
0. I kind of move up a certain distance of, to get from here to where that slice starts. I don't know how far I've moved up, but it's got to be some distance in terms of what? Y. Okay? All right, things are starting to get fun. Right here, guys, do you see kind of, and again, think of this slice as really, it's kind of like a line right here. All right, we kind of exaggerated it a little bit so we understand what variable we're working with. But guys, the thickness of this slice is really about what value?
0.
0. Okay, so what we really kind of have here, guys, is similar triangles. So pretend this right here. What's this x really kind of correspond to?
80.
80. All right. Then the height of the big triangle is 55. What's the height of the smaller triangle in here then? That's given from the top point down to this slice.
55 minus 1.
Okay, so I'm going to put that in here. So from here to here, we pretty much have a height of, the overall height was 55. We took out a distance of y, so this height must be 55 minus y. So I always think it's important after you have a cross section here to set up a similarity ratio right away. And I'll show you why here in a second. So would you guys agree this horizontal distance x really corresponds to what?
80.
So from this we get x is to 80 as, okay, what's the height of the smaller triangle?
55 minus 1.
Over a height, or of the larger triangle?
55.
Okay, here's the deal. We're really close to having this done. Guys, when you've kind of figured out where your slice is going to go and what kind of slices you're going to have, we've got to start thinking, okay, if I can find the volume of one slice, then it basically becomes a definite integral for all slices, bottom to top. So here's how this works, kids. Your first goal all the time, your first goal write a function for the volume of, for the volume of one slice. Okay. So let's go into this right here, kids. That slice that we're kind of talking about in this pyramid might be right in here. Right?
That sounds fun.
You like that?
Yeah, filled in right.
Okay. Based on our cross section down here, what distance is this really?
80.
Okay, the very bottom it's 80, but as I move up, these distances are getting smaller and smaller and smaller, aren't they? What did we call that in this section?
X.
Okay. But if we said all these cross sections are going to be little squares that fill this up in here, because wouldn't this distance right here, if I cut right there, if I cut perfectly through, wouldn't the distance going this way then have to be the same as this for that square? Okay. So this would have to be x right here also, wouldn't it? Okay, let's talk about the volume of this one slice. This is kind of like a rectangular prism that really has a height really close to what value?
0.
0, okay? Would you guys agree that that's really a rectangular prism? Has a length and a width and a height? Or a square prism, if you will? Well, guys, if I want to go ahead and write a function for the volume of one slice, I'm going to write it this way right here. The volume of one slice, I'll write it V slice. Okay. Wouldn't the volume of that be length, x, times width, x, times our height that we called right here, kids? What are we calling the height right here that's really close to 0? Delta y right here, or change in y. So our volume of one slice here, guys, becomes x to the second power, x times x. That's the length times the width times the height of that really thin piece. Becomes x squared times delta y. Okay? All right, we're really close here. Which variable has the delta symbol with it? Y does. Okay? So the way this works is as follows. We have to write our function for one slice as a function that's dependent upon all y's. I can't do that just now because what variable is still in here with delta y? X squared, right? It would sure be nice if I could replace that x with something, wouldn't it? Okay, so look right here. Could I get x alone right here? Hey, help me out with the similarity over here. Based on cross multiplying and dividing, x would equal, all right, I'm going to put the 55 minus y in parentheses. Is that okay with you guys? We would call that 80 times what?
55 minus 1.
All over what?
55.
Okay, are you with me on that? Okay. So I want to replace that x, anywhere where I have an x, I want to replace it with this mess right here, right? You guys agree with that? Okay, so what I could say right here then is the following. I could say the volume of one slice then, because let's face it, we're replacing x so I can get what variable into the problem. Okay, so the volume of this slice, and this is your most important part right here. If you can get to this point right here, volume of one slice, you're in good shape. The volume of one slice would be the following. What are you going to replace with x?
80 times 55 minus y over 50.
Okay, so it's going to look like this. 80 times 55 minus y all over 55 to what power? Times what's the height here then?
Delta y.
Okay. That's just the volume of what?
The slice.
One slice.
One slice.
Now, like we were talking about two-dimensional integration right here, we could find the volume of one bar, but if I want the total area, we want the addition of all bars. Or basically it became the definite integral from your lower limit to your upper limit. So think about this. Which variable is driving everything here now, guys?
Delta Y.
Okay, once you have your slice, you've got it. Okay, because now you can write a function for your total volume. And this is how it works. This is where we want to get to. This is the end game. The total, my friends, will equal the definite integral of all those slices. So think about my pyramid. This pyramid starts at ground what? And it has a height of what? It's like we're going to take 0 to 55 inches of all of these little pieces of paper stacked up. So my limits, do you understand? 0 to 55. Or think about this. If y is driving everything, my y value is on a scale from here to here, or what distance?
55.
Okay, so we're going to say that the total becomes the integral of 0 to 55 of your function that you have up here for one slice. It's just the summation of all the slices put together to get your volume. Okay, so you're going to have 80 times 55 minus y, all over 55, squared. Here's the deal. Once you come to the total right here, this delta y is a summation of all of them, so it means all of y, so you're going to have your dy out here. The delta y basically turns into dy for you. Now what's cool about it is this. Once you have that set up, you're like, okay, what's the value here? Well, by formula, what did we already know the value was going to be?
117,333 and 1/3.
Exactly, 117,333 and 1/3. And that should be a cubic inches because it's volume, right? I messed that up. That should be a 3. Okay. Check this out. We're going to go to Desmos. We're going to get rid of this. We're going to get rid of this. We're going to get rid of this. I'm going to type in INT. Whoops. Okay, sorry, Brett Favre, INT. 0, tab, 55. Tell me what to type in.
80 times 55 minus y. Oh, divided by 55. Squared.
What do you want to put at the end here?
dy. Wow, that's crazy.
Should we get the same thing?
Yeah,
Isn't that pretty cool?
it's amazing.
I think it's pretty cool. In fact, I think it's amazing. In fact, you know what? What we're going to look at tomorrow, probably in that bottom example, I'm probably going to say that bottom example for tomorrow so everyone's here because it's a doozy. Guess where that formula came from in order to be able to find the volume of pyramids? This concept right here. This concept is what defined the formula for the volume of any pyramid with base, or I should say any square pyramid with base B and height H. Okay? Take a look at your second problem that we're going to talk about. What's it say there?
Cone. Show that the volume of any cone with radius r and height h is 1/3 pi r squared h.
The volume of any cone is 1/3 pi r squared times height. But we need to prove that that's true by saying, well, think about a cone. That's just a bunch of what stacked on top of each other? A bunch of circles stacked on top of each other. Where the circles, as I start at the bottom, and what's going to happen to the size of the circles as we move to the top in the cone?
Smaller.
They're going to get smaller, 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 and smaller. Okay? We're going to show how that formula came about based on this concept here. And we'll look at that tomorrow. Okay? What I want to do then is this. We want to stay with this idea. We're going to skip ahead. We're going to skip around a little bit. But guys, what did we get for a value here again?
17,000.
Same thing. Okay, the volume is 117. What was it? 333 and a third, kiddos? cubic inches, okay? Now, we're gonna spend some time in this section, but man, I tell you what, that is cool, okay? That's just cool stuff. I think that's so cool, all right? Is that the most difficult thing you've seen today? No, yes? Yes?
Yeah.
Oh, let's look at some more. I'm excited about this. Go to page 2 there, kiddos. Let's go to page 2 and see what we can come up with. Okay, we'll come back to this one tomorrow. We'll get through one more example probably today. We'll come back to this tomorrow. The fact that we're not going to get through notes today, what's that mean assignment-wise?
None.
I'm sorry. Okay. Let's talk about this one here, kids. I'm going to kind of use Desmos to help us visualize this a little bit. But it says find the volume of the figure bounded by the region of the what?
X and Y axis.
X and Y axis. X equal 4 and what else?
Y plus X squared plus 3.
And it's rotated around the left.
X axis.
Okay. We need to make a pretty good sketch here first. So we know we've got an X and Y axis for boundaries, don't we? Okay, let's just do this. Let's make a sketch first. Anytime you see something like this, we're going to sketch this. Okay? So here's the deal. The X and Y axis were two boundaries, weren't they, kids? All agree with that? Okay, what's another boundary line?
X equals 4.
Wouldn't X equal 4 go over here to the X axis at 4 and be a vertical line right here? What value is this for X over here then, really?
0.
Guys, it says another boundary line is what? So if I plug 0 in for X, what would you get for Y? 3. So this is going to start up here at 3. And what if I put 4 in there? What's 4 squared? Plus 3 more would make 19, wouldn't it? So 19 is kind of up here. And guys, isn't this a parabola? So wouldn't this kind of shape concave up to that point right there? Okay. So I'm going to highlight the bounded area we're really talking about. So here's the deal. These are our boundaries. There's the X and Y axis. Here's X equal 4. And here's the X squared plus 3 right there. Okay? Now, it says we're going to take that shape and we're going to rotate that around the what?
X axis.
So around the X axis. So we're going to say, oh, okay, let's take this and rotate it around that axis right there. Going to rotate around the axis. So this is going to kind of flip down there, okay? That makes sense to you? Okay. Here's the big part about this right here. When you are slicing, and maybe I should ask the question, can you guys kind of visualize what this is going to look like here when you do it? Or when you rotate it? You ever see bowls that are kind of shaped like like this here a little bit? Or a vase that's shaped like this? It's just going to be kind of on its side. Can you guys kind of visualize that? And this is going to be a solid piece though. Okay? Here's the big idea. When they tell you you're going to rotate around the x-axis, I'm going to give you a note. Your slices should be, what's this symbol mean? Perpendicular to your axis of rotation. Okay. In fact, I was going to try and find a picture in my book. See if they had this. They might. Actually, let's let me Google one up. Maybe I can see solid of revolution for x squared plus 3. my friends, we might get something that looks something kind of like. Right here almost, okay? It's gonna look kind of like this right here, but instead of being straight right here, you see how this is straight right here and it's a solid piece right here? This would be more, you guys kind of see the curved part there? You guys get what that looks like? Okay, so here's the deal, kids. On this right here, we're gonna put a slice perpendicular to which axis? Which axis you're rotating around? Okay. So I'm going to make my slice right here. Okay. Put our slice right there. Okay, so let's talk to me about this. Again, the thickness of this slice, really thick or really small? Infinitely close to what value? 0. Now guys, the thickness of this, is this a vertical thickness or a horizontal thickness?
Vertical.
Okay, it's a vertical slice, right? But the thickness here goes left to what?
Left to right.
Okay, so we would call the distance right in here, we would call this distance right in here delta, it's left to right, x, right? Okay. Then, do you agree the height of this right here? The height of this would be some value of what? Y. You okay with that? Okay, now when I start spinning those little slices around the x-axis, what kind of shape are you going to make? You know what? I have these burrs. I start spinning these around the x-axis. Can you kind of visualize these pieces? Getting larger as I move left to right. Okay. These are going to be little, what shape is this? Little cylinder then, right? You guys recall the volume formula for a cylinder? How about I help you? The volume formula for cylinders, this is going to involve cylinders. Cylinder slices have a volume, pi r squared times the height. Okay? So let's talk about the volume of our one slice. Guys, wouldn't the radius really, if this is my axis of rotation, wouldn't the radius really, there's an axis kind of going through this right here, wouldn't the radius really be that height of y? Okay, so wouldn't the volume of one slice right here, kids, equal pi? What are you calling the radius here, kids? So pi times y squared, that's the radius, times the height. What's the thickness of this thing, or the height of this cylinder? Delta what? Right? So based on the volume of that one slice, kid, we've got to ask ourselves the question, which variable is driving the answer for this? X or y? X is. We've got to get this y out of here. We've got to get this y in terms of what? Well, guys, it's pretty cool. They tell you right up here, y is equal to what? What can you replace y with now? Okay, so the volume of your slice, all in terms of x, your volume of your slice is going to equal pi times, what's going in for y's, guys? All to what power? Delta x. If you've gotten your slice in terms of the right variables, then your job here, simply put, is to say, okay, now I can go to my total integral to get a value. So my total will equal the definite integral from, okay, look at the x-axis that we're working with. We're using x values, so what are the limits on the x based on our sketch? Starts over here, doesn't it? Ends where? So we've got limits 0 to what? Of your function, pi times x squared plus 3 all to the second power Then delta x turns into what when you have the summation of all of these?
Yeah.
And once you've set it up, I can make you do it the long way, or I can say go to the calculator and punch it in. Where are you going? Okay, so let's look. We're going to jump into the Desmos. You guys are going to tell me what to type. Oh my gosh, this is so cool. Okay, so we're going to go integral. What are our limits?
4, 0, following, parentheses, x squared plus 3, squared, yes.
And by golly, kids, what do you think? What do you think the value of that figure is when you rotate it around the x-axis?
1,158.6.
Yeah, and I think going two places is good. So 1,158 point. Yep. Where'd I set the pen down at, kiddos?
Is it right
Here
there?
it is, yep. Thank you. Okay, so the volume right here. What was it, 1,158.62?
Mhm.
Since it's a volume, what type of units, kids? Cubic units. All right, I think that's probably a pretty good place to stop because I know I can't have enough time to get through the next ones with you, so we're going to pick up the rest tomorrow. Right? Man, lots of good stuff going on here, so you might not think that, but this is so